Okay, so welcome back. We restart. So the last seminar of the day is by Edward Witten from Princeton, and the title of his seminar is Algebras and Entropies for Black Holes and the Theta Space. So Edward, please.
Well, thank you very much, Mark, for the invitation and the introduction. Sorry for a short interruption at this end. So I'll start with a general introduction about black holes and thermodynamics. Then I'll talk about two papers. One is the paper I've indicated on gravity and the cross product. The second is a paper which I think will be in the archive tomorrow with the co-authors I've listed. Now, because of time constraints, I'll mostly just explain the context rather than a lot of technical details. The idea of black hole entropy goes back to Jacob Bekenstein, who was inspired by questions from his advisor, John Wheeler, and he asked what the second law of thermodynamics means in the presence of a black hole. The second law for an ordinary system says that entropy can only increase. But if we toss a cup of tea into a black hole, the entropy seems to disappear. Bekenstein wanted to generalize the concept of entropy so the second law would hold even in the presence of a black hole. For this, he wanted to assign an entropy to the black hole. Well, what property of a black hole always increases? It's not true that the mass always increases because, for example, if you have a spinning black hole and it absorbs counter-rotating matter and to reduce its angular momentum, the black hole mass can actually go down. But at this time, Hawking had just proved the black hole area theorem that says that the area of the black hole horizon can only increase. So it was fairly natural for Bekenstein to propose that the black hole area is a contribution to the entropy. He proposed a generalized entropy of a black hole, which was the area over 4G h bar plus S out, where S out is the ordinary entropy of matter and radiation outside the black hole. And actually, the coefficient of 4 was not part of Bekenstein's original proposal. The factor of 4 was a later contribution by Hawking. But anyway, Bekenstein proposed that it's the generalized entropy that the second law applies to. The generalized second law is supposed to say that the generalized entropy always increases. Stephen Hawking supposedly was skeptical of Bekenstein's idea and set out to disprove it by studying the behavior of a quantum field interacting with a black hole. But in the process, he ended up proving that Bekenstein was right. He found that quantum mechanically, the black hole is not really black, but has a temperature of order h bar. An observer way up here at future infinity, up here, sees thermal radiation coming out of the black hole. And taking that into account and applying thermodynamics, Hawking, first of all, concluded that Bekenstein was right about the entropy being a multiple of the area, and secondly, determined the precise coefficient. Soon afterwards, Gibbons and Hawking considered another situation with horizons. This was cosmology rather than black hole physics, and proposed that also the area of a cosmological horizon is a kind of entropy. More specifically, they assigned a temperature and an entropy to the region of de Sitter space accessible to an observer. So de Sitter space is the maximally symmetric solution of Einstein's equations with a positive cosmological constant. This is one way to write the metric. It expands exponentially when the time goes to plus or minus infinity. And this metric in the future may be a good approximation to the real world. Because of exponential expansion within roughly 10 to the 11 years, galaxies that aren't gravitationally bound to the Milky Way will be out of sight behind a cosmological horizon. A picture describing this is as follows. What I've drawn here is a Penrose diagram for de Sitter space, where time runs vertically. Time runs vertically and space runs horizontally. In this picture, the observer, us, is on a geodesic that's represented by a straight line at the edge of the diagram. The green region is what's called the causal patch. It's the region of de Sitter space that you can influence and you can also observe as an observer in de Sitter space. So the part of de Sitter space that's causally accessible to an observer in the far future is this region. Well, let me say it better. In the far future, it's believed our universe will be a lot like de Sitter space, and the portion of the universe accessible to us will be, to a good approximation, this green region. The green region is bounded by past and future horizons, and Gibbons and Hawking attributed to the cosmological horizon an entropy A over 4G and a corresponding temperature, which actually had been defined earlier. The meaning of the de Sitter entropy has been a mystery ever since. Well, many researchers have thought that somehow the entropy A over 4G of the black hole or cosmological horizon means that the horizon can be described by some sort of degrees of freedom that live at its surface with 1 bit or qubit for every 4G of area. For instance, in a famous article in 1992, John Wheeler illustrated that idea with this picture, where he visualized the black hole horizon as a sphere divided in little units of area, each having a bit or qubit. Well, as I said, the article was published in 92, but Wheeler had been Bekenstein's advisor, and I tend to believe he'd been drawing this picture for 20 years. More modern understanding of black hole entropy involves a better quantum mechanical definition of entropy. Classically, you might consider n particles in a box with positions x and momentum p. As a classical physicist, Boltzmann assumed that at a given time, x and p have definite values, even if you don't know them. Then you could describe the state of your knowledge by a probability distribution function rho. And ultimately, Boltzmann and his successors, such as Gibbs, defined the entropy as the phase-space integral of minus rho log rho. Note, though, that for dimensional reasons, there's an overall ill-defined additive constant in this formula. dp dx is dimensionful, and if you change units, it'll be rescaled. You could compensate by rescaling rho, but then the logarithm shifts by a constant. So classical entropy has an ill-defined additive constant, which I'm mentioning because later we will get to a version of quantum entropy with a similar ill-defined additive constant. The quantum analog of the probability distribution function rho of p and x is the density matrix rho of a quantum system. So the quantum version of the Gibbs formula is the von Neumann entropy of the density matrix minus the trace of rho log rho. In the classical limit, the von Neumann entropy goes over to the classical entropy, except that it fixes the constant that was ill-defined classically. But there's a basic difference between the classical and quantum cases. Classically, one believes x and p have definite values and one uses a distribution function because of lack of knowledge. So the entropy reflects lack of knowledge. Quantum mechanically, if a system is entangled with something else, a mixed state density matrix rho is the most precise description that quantum mechanics allows. And therefore, there's an irreducible fine-grained entropy, even if we know the state of the system as precisely as possible. This has no classical analog. The first to interpret the Bekenstein-Hawking entropy in terms of entanglement entropy was apparently Raphael Sorkin in 1983. His idea was the following. In a quantum field theory, divide space into two regions, A and B. In the application, B is going to be the region behind the horizon, and A is the region outside the horizon. But in the general discussion, A and B could be anything. Let psi be a state of the system. For example, psi could be the vacuum state. And let rho A be the density matrix of the state psi for measurements in region A. You can try to calculate its entropy minus trace of rho A log rho A. Sorkin found that this entropy is ultraviolet divergent for any state psi, and the coefficient of the leading divergence is proportional to the area, capital A, of the boundary region between the two regions, A and B. So the reason that the coefficient of the leading divergence is proportional to the area of the boundary is that the leading divergence comes from short distance behavior near the boundary. High energy modes near the boundary, entangled between modes just outside and just inside the horizon, contribute this leading divergence. And since they could be anywhere on the boundary surface, you get a result for the entropy proportional to the area. Well, instead of rejecting this because it was ultraviolet divergent, Sorkin, published it with the suggestion that somehow gravity would cut off this ultraviolet divergence, leaving an entanglement entropy in the vacuum between the two regions. That would be A over 4G, where A is the area of the boundary between them. In other words, Sorkin had ignored gravity, so effectively Sorkin had G equals 0, where G is Newton's constant. Sorkin's idea was that the correct answer was A over 4G, and he was getting A times infinity because of trying to set G to 0. Sorkin's idea makes a lot of intuitive sense as it matches two ideas. One is that A over 4G is the irreducible entropy for someone who has access only to the region outside the horizon. Second is that the divergence in the entanglement entropy, as I said, is proportional to the area because it comes from short wavelength modes near the horizon, as if after cutting off the divergence, the density of quantum degrees of freedom per unit area is 4G, as in Wheeler's picture. So this was 1983, and the next development I'll mention was a decade later by Susskind and Uglum. They made a simple observation that strongly supports the idea that S out should be entanglement entropy. So, okay, remember, for Bekenstein, the generalized entropy was A over 4G plus S out, where S out was supposed to be the ordinary entropy outside a black hole. And Bekenstein assumed in all his discussions that thermodynamics was valid, and S out was thermodynamic entropy. However, thermodynamics isn't always valid. And Sorkin's proposal was in a situation where you wouldn't use thermodynamics. The state was just the vacuum state. And the entropy was completely this quantum entanglement entropy. Susskind and Uglum, so generalizing that, one might think that S out should always be von Neumann entropy. It has the advantage that the formula is then always defined, rather than being only defined when thermodynamics is valid. And ultimately, although I won't explain that today, Aaron will prove that the formula is true in general, whether thermodynamics is valid or not. But anyway, Susskind and Uglum's observation was that if we interpret S out as entanglement entropy, then the generalized entropy is better defined than either term is separately. The second term has an ultraviolet divergence that Sorkin had noted. But actually, Susskind and Uglum points out that the first term also has an ultraviolet divergence, namely the divergence in the relation between the bare Newton constant G0 and the physical observed Newton constant G. In Hawking's calculation, he was working at lowest order in gravity, so the G that entered his calculation was the bare Newton constant. But for Bekenstein, he presumably was talking about the physical observed G. So between Hawking's calculation and Bekenstein is the renormalization of G, which in one loop order looks like this, where lambda is an ultraviolet cutoff. And Susskind and Uglum pointed out the simple but beautiful fact that the coefficient of the quadratic divergence in the normalization of Newton's constant precisely cancels the coefficient of the leading divergence that Sorkin had found, so that the generalized entropy is better defined than either term is separately. And these arguments were refined later and have stood up well. So 21st century developments have strongly supported these ideas, but leaving plenty of mysteries. In the time available, I'm only going to talk about one aspect of the story. Why is it that entanglement entropy is ill-defined in quantum field theory, so that S out has that quadratic divergence that Sorkin pointed out, but becomes well-defined once gravity is included? So I'm going to give a somewhat abstract answer to this question in the remaining time. First of all, in ordinary quantum mechanics, when one considers the entanglement between systems A and B, one normally assumes at the start that each system has its own Hilbert space, HA or HB. The combined system then has a tensor product Hilbert space, HA tensor to HB. A state in this combined Hilbert space might be a simple tensor product of states psi A and psi B. In that case, systems A and B can separately be described by pure states psi A and psi B, and there's no entanglement entropy. But more generally, psi AB might be an entangled state, not a simple tensor product, but a sum of tensor products. In that case, we say that systems A and B are entangled. And for example, for such a psi, system A would have this density matrix, and its entropy would be minus the sum of pi log pi, which will always be positive, except in the case of a pure state, where one of the p's is 1 and the others are 0. The point of this is that in ordinary quantum mechanics, whether or not a state has a non-zero entanglement and entanglement entropy is a property of the state. That's not so for entanglement entropy between different regions in quantum field theory. As the divergence found by Sorkin was an ultraviolet divergence, as I explained, and since every state looks like the vacuum at short distances, this divergence did not depend on the state. The root of the problem is that it's not true that there are separate Hilbert spaces HA and HB for the inside and outside regions. There's only a combined Hilbert space H for the whole system. What the separate systems A and B have are not Hilbert spaces HA and HB, but only algebras of observables, curly A for region A and curly B for region B. These algebras act on curly H, so they can be defined to be von Neumann algebras. A von Neumann algebra is just an algebra of bounded operators on a Hilbert space that's closed under a certain type of limit. Now, I'll give you some more detail in a moment, but first I'll just give an overview that there are three broad types of von Neumann algebra. A type 1 algebra is the algebra of all operators on a Hilbert space. In ordinary quantum mechanics, when we discuss the system A, it has a Hilbert space HA, and the algebra of observables of the system is the algebra of all operators on HA. That's of type 1. If a system is described by type 1 algebra A, then it can have quantum mechanical pure states, namely states in the Hilbert space in which A is the algebra of observables. One can also define density matrices and entropies for a system that has such an algebra of observables. And the other types are less familiar. So I will explain what the other types are in a little bit of detail, but first I'll tell you the bottom line. A type 2 algebra does not have pure states, but it does have density matrices and entropies. A type 3 algebra is the worst type. A system whose observables form a type 3 algebra does not have pure states and also does not have density matrices or entropies. In the early work on von Neumann algebras in the 30s, Murray and von Neumann struggled for quite a while with the question of whether type 3 algebras exist or not. They did not find it easy to give an example. However, by now you might anticipate the bad news, which is that a rich source of examples is provided by quantum field theory. In quantum field theory, the algebra of observables of a region of spacetime, like one of the regions considered by Sorkin, is always of type 3. So to a region, one can never associate a pure state or a density matrix or entropy. The statement that the algebras are type 3 goes back to Araki in the 1960s, and it can be viewed as an abstract explanation for the universal ultraviolet divergence of the entanglement entropy. However, and this is the main idea that I want to explain in the rest of the talk, it turns out that including gravity in a semi-classical way changes the picture. At least in the case of the black hole or de Sitter space, including gravity at a semi-classical level changes the algebra of the region outside the horizon from type 3 to type 2. I don't claim to know what would happen if you include gravity exactly, I also don't know for sure whether there's a similar answer in more general spacetimes with horizons. For the moment, this is just a story about the black hole or de Sitter space. So when gravity is turned on semi-classically, the region outside the black hole or de Sitter horizon is described by an algebra in which entropy is well defined, though there's no notion of a quantum mechanical microstate. We can interpret that as a somewhat abstract answer to the question of why including gravity suddenly enabled us to convert the ill-defined divergent S out into the better defined generalized entropy. But to understand how this works, we need to understand something about these von Neumann algebras of type II and type III. What are they? Well, they can be most simply described as the algebras that act on certain thermal systems. A finite thermal system A with Hamiltonian H and inverse temperature beta has the density matrix rho beta, which is 1 over z times e to the minus beta h, where z is such that the trace of rho is 1. Roughly speaking, the thermal field double of a quantum system is a pure state of a larger system with density matrix rho beta. But this isn't so precise in the limit of an infinite system. Something that our textbooks on quantum statistical mechanics usually don't explain well is that this definition of the density matrix is fine for a finite system, but it doesn't behave well in the thermodynamic limit because z is divergent usually in the thermodynamic limit. And the Hilbert space itself doesn't usually have a thermodynamic limit because in the infinite volume limit, a Hilbert space that would contain all the typical states of a thermal system would have to have an uncountable dimension. And it's usually not useful to formulate physics in a Hilbert space with an uncountable dimension. What the thermal field double state does is to enable you to take the infinite volume limit in a separable Hilbert space, a Hilbert space of countable dimension. And in particular, the thermal field double construction gives you a Hilbert space that does have a thermodynamic limit, unlike the Hilbert space of a single system. To define the thermal field double for a finite system, we simply introduce a second copy B of the original system with an identical Hamiltonian. And then if the original system had eigenstate psi I with energies EI, we define the thermal field double state by this simple formula. So the point of the formula is that psi TFD, the thermal field double state, purifies the thermal field double density matrix rho beta, since if little a is an operator on system big A, its expectation value in the thermal field double state, after summing over the unobserved states of system B, is given by the appropriate thermal expression. Now, this formula is not really well defined for an infinite system, since Z is infinity and the sum doesn't converge. But it turns out that in an appropriate sense, the state psi TFD does have a thermodynamic limit. But funny things happen to the algebra of observables in the thermodynamic limit. That's where algebras of type II and type III come in. Well, the simplest Hamiltonian of all is 0. So let's first discuss the case of a qubit system with a Hamiltonian of 0. For a system of n qubits with Hamiltonian 0, the partition function is just 2 to the n. And the thermal field double state is just a completely entangled state of system A with a second system B, also consisting of n qubits. So this is the thermal field double state. The nth qubit of the first system is completely entangled with the nth qubit in the second. Let A and B be operators that act only on the first k spins of system A for some k no bigger than n. I think my notation is unfortunate because B acts on system A, not on system B. So it would have been better if I called B A prime. I'd intended to make that change in the slides before today's talk, but I guess I forgot. So A and A prime are operators that act on system A, but they only act on the first k spins of system A for some k. Define a function f of A, which is the expectation value of little a in the state psi. Well, you can see that, first of all, f of 1 is 1 because the state psi is properly normalized. But secondly, here on this page, I did replace b by a prime. Secondly, f of a prime is f of a prime a. The reason is that the density matrix is 2 to the minus n times the identity. So f of a prime is the trace of a prime times rho, but that's just a C number times the trace of a prime. So there's a factor 2 to the minus n, which will go to 0 for large n. But for any finite n, that factor is just a finite number. And therefore, we deduce this formula by that computation. But moreover, the function f of a has a thermodynamic limit because the expectation value of a in the state psi is well defined as long as we include in psi all the qubits that a acts on. But if we include any extra qubits, that doesn't affect the expectation value of the operator a. The extra qubits just have some normalized state. So it doesn't affect the expectation value of a. So this function a has a thermodynamic, this function f of a has a thermodynamic limit. And in the thermodynamic limit, it still obeys this relation because it obeyed it for every n. And it's positive in the sense that f of a dagger a is positive for all non-zero a because that was true for every n. And again, there was a thermodynamic limit. Well, so far we've defined the function f on the whole algebra a naught of all operators that act on only finitely many qubits in system A. By taking the closure of a naught in von Neumann sense, which means we allow certain operators that act on arbitrarily many qubits, but with matrix elements that decay rapidly for large k, we can complete a naught to a von Neumann algebra A, still with a function f of a that has the same properties I've stated. Since f of a prime equals f of a prime a, this function is usually called a trace. And I'll formally denote it as simply the trace of a. But it's not the trace of a in any Hilbert space representation. It's more like a normalized trace with an infinite factor of 2 to the n removed. Remember, we defined f of a as an ordinary trace, but we had to divide by 2 to the n. And then since we took the limit when n went to infinity, f of a is a normalized trace with an infinite factor removed. So we found an example of an algebra that has a trace. But you could say that we know a more elementary example of an infinite dimensional algebra with a trace. This is the type 1 algebra B of all operators on an infinite dimensional Hilbert space curly H. It has a trace, but the trace isn't defined for all elements of B, only those that are trace class. For example, the identity element of B does not have a trace, or its trace would be infinite. Whereas, here, we defined a trace that was well defined for all elements of the algebra, and the trace of the identity was 1, not infinity. So the algebra we've defined is a fundamentally new algebra in which every element has a trace. In fact, it's the simplest example of a type 2 algebra. It's said to be of type 2-1, and it was first constructed by Murray and von Neumann in essentially the way I've explained. If A is the type 2-1 algebra we just constructed, and B is the other algebra you all know about, the type 1 algebra of all operators on an infinite dimensional Hilbert space, we can make a third type of algebra by simply taking their tensor products, A tensor B. This new algebra C still has a trace since each factor does, but it's not defined for all elements because of the factor of B. In fact, C is a new kind of algebra said to be of type 2 infinity. It turns out that A and C are the important types of type 2 algebras for our applications. C is related to the black hole and A is related to de Sitter space. Well, I've told you how to construct type 2 algebras. What would be a type 3 algebra? To get type 2 algebras, we started with a Hamiltonian of 0. If we take almost any non-zero Hamiltonian, then in the thermofield double, then in the thermodynamic limit of the thermofield double, we're going to get a type 3 algebra. The simplest case is a Hamiltonian that's a sum of single qubit operators. For instance, a sum of single qubit operators of this form. At inverse temperature beta, the ith pair of spins would be entangled fully but not maximally in the state that I've indicated here. We can still define a state psi TFD for n qubits by entangling each qubit pair in that state. Then we can define the function f of a as before, and as before it has a thermodynamic limit. The important difference is that f of a prime is not equal to f of a prime a. For n going to infinity, we can define an algebra A naught consisting of operators that act on any finite set of qubits of the A system, and its completion is now a von Neumann algebra of type 3. Algebras of type 2 or type 3 do not have an irreducible representation in a Hilbert space. Whenever such an algebra acts on a Hilbert space curly H, it always commutes with another algebra of the same type. For example, we constructed our type 2 and type 3 algebras as algebras that act on the A part of a bipartite system AB. So in that construction, they commute with an identical algebra that acts on system B. The difference between a type 2 algebra and a type 3 algebra is that a type 2 algebra has a trace and a type 3 algebra does not. Moreover, in a type 2 algebra, the trace is non-degenerate in the sense that the quantity, the trace of AA prime, can be viewed as a bilinear form on the algebra. It's non-degenerate and positive definite. Positive definite means that the trace of A dagger A is positive for all non-zero A. So if f of A is any linear function of A, it's of the form trace of AA prime for some unique A prime in the algebra. Now let's go back to the situation considered by Sorkin with the region behind the horizon and the region outside the horizon. We consider some state psi of the whole universe. Suppose it were true that physics in region A is described by a type 2 algebra curly A. Then the linear function that takes A to its expectation value in the state psi would be equal to the trace of A times rho A for some rho A in the algebra. If the algebra were type 1, we would use this condition to define the density matrix rho A of state psi for measurements in region A. So it makes sense to call rho A the density matrix also in the type 2 situation. Once we have density matrices, we can define entropies as well. So if the region outside the horizon is described by a type 2 algebra, then we can define an entropy for this region. As I've already explained, in ordinary quantum field theory, the algebras are type 3. But it turns out that when we include gravity, things are different. Gravitational effects, even for very weak coupling, convert the type 3 algebras into type 2 algebras. The mathematical mechanisms that lead to this are quite simple and have been known for roughly half a century. What's known is only that these mechanisms are actually implemented by perturbative gravity in the field of a black hole or de Sitter space. The details are different in the two cases, and I will have time only for very brief explanations. So here's a Penrose diagram of the maximally extended Schwarzschild black hole in asymptotically flat space-time. The black hole is a wormhole between two asymptotically flat universes, which we will think of as the two systems A and B. In low energy effective field theory, we would construct a Hilbert space H for the black hole spacetime. We construct it by taking fields in the whole spacetime on a Cauchy's hypersurface of the whole spacetime. We quantize those fields and we make a Hilbert space. So the Hilbert space describes what can happen in region B and also what can happen in region A. This Hilbert space is acted on by regions curly A and curly B of operators in this region and in this region, respectively. So we're considering an observer way out here. So A is the region outside the horizon, and curly A is the algebra of observables outside the horizon. Now, two important operators are the ADM energies, H right and H left, measured on the right or left sides. The important difference between gravity and ordinary quantum field theory is that in gravity, those are well-defined operators that can be measured by an observer at infinity. But in ordinary quantum field theory, only the total energy is well-defined. There's no way to separate it into energies on the two sides. So it'll take some elaboration, but this is the key difference between gravity and ordinary quantum field theory. Another important operator, which is well-defined in ordinary quantum field theory, is the bulk operator, little h, that generates the killing vector field of the spacetime. The killing vector field moves time forward on the right and moves time backward on the left. So that's a symmetry of the spacetime. And in ordinary quantum field theory, that will correspond to a conserved quantity, which I'm calling little h. These operators are related by little h being beta times big H right minus big H left, where beta is the inverse of the Hawking temperature. So in ordinary quantum field theory, little h would be an observable, but it's an observable if you have access to the whole universe. It's not an observable if you just live on one side. With gravity, H right and H left are separately observables, one to an observer on the right, one to an observer on the left. So gravity enables you to make this splitting that you would not have in ordinary quantum field theory. There's a subtlety about constructing the Hilbert space H of gravitational fluctuations. If we look only at gravitational fluctuations that can be measured locally, we get a Hilbert space H naught of graviton modes that's similar to any usual quantum field theory Hilbert space. An algebra, which I'll call A right 0 of observables outside the horizon, acts on H0. It's a type 3 algebra as if gravity were any other quantum field. But there's one more mode of the gravitational field that isn't locally measurable and isn't included in H0. It's a relative time shift between the left and right-hand sides of the black hole. You see, now what? Okay. Wrong talk. That was unfortunate. Okay. You can have a gravitational perturbation which is localized and which has the property that can be removed by diffeomorphism, but not by diffeomorphism that's trivial at infinity. Only the diffeomorphism that shifts the time of an initial value surface measured at infinity. So there's a mode in gravity, which is a shift in the time measured on the right relative to the time measured on the left. Neither time is really intrinsically well-defined because the space-time has a symmetry that moves time forward on the right and moves time backward on the left. So what's well-defined is really only the sum of the two times measured on the right and on the left. But that sum is a well-defined time shift variable delta that nobody can measure. It's not measurable on the right, it's also not measurable on the left. But when we construct the Hilbert space of gravitational fluctuations in the field of the black hole, we get a Hilbert space similar to what you'd have in any quantum field theory, tensored with L2 of R, where L2 of R is the Hilbert space of functions of the time shift. We can use the time translation symmetry of the black hole background to reduce to the case that the time measured on the initial value surface on the right-hand side is 0, and then delta will be the time measured on the left side. So compared to an ordinary quantum field theory in the black hole background, gravity in the black hole background has a slightly bigger Hilbert space, where you tensor with one little bitty extra factor, L2 of R, And likewise, in gravity, there's one operator that's measurable by an observer on the right of the horizon that doesn't have an analog in ordinary quantum field theory. This is the ADM mass h right at infinity. So now this formula that the killing vector conserved charge is beta times h right minus h left is key. I'll write the formula in this form. H right is 1 over beta times little h plus h left. The operator h left acts on the time shift, delta L, as the generator of time translations. Up to a unitary transformation, we can assume that HL acts only on the time shift. Since if you think that HL also acts on the Hilbert space of ordinary fluctuations, you could remove it by a unitary transformation. So up to a unitary transformation, HL acts only on the time shift. Now let's look at this formula here. On the right-hand side, little h over beta acts only on the Hilbert space of ordinary excitations. HL acts only on the time shift. H is what's called the modular Hamiltonian of the Hartle-Hawking state in H naught. The Hartle-Hawking state of a black hole is the thermophile double state. For de Sitter space, it's sometimes called the Bunch-Davies state. H is the modular Hamiltonian of that state. Okay, there isn't really time for an explanation, but as shown long ago, the statement that little h is the modular Hamiltonian is a fancy way to describe the fact that the black hole has a Hawking temperature 1 over beta, and similarly for de Sitter space. Now, what I've explained is that the algebra of observables to the right of the black hole is almost the same as the ordinary quantum field theory. It's an algebra A right 0 of type 3 that acts on H0, but it's got one more generator, which is this H right, or otherwise H over little beta plus H left. So the Hilbert space is just a little bit bigger than it would be without gravity. Or if to say better, the Hilbert space is just a little bit bigger than it would be if gravity were treated as an ordinary quantum field. It's bigger because there's this one extra factor of L2 of R. And also the algebra of observables is just a little bit bigger with one more generator. Well, what we've rediscovered is the cross product of the algebra AR0 by its modular automorphism group in the language of operator theorists. In the 1970s, Takasaki and Kahn discovered that if one starts with a type 3 algebra, this construction gives a type 2 algebra. From their point of view, that was useful because type 3 algebras are hard to study. Type 2 algebras are much easier. This way to construct a type 2 algebra from a type 3 algebra gave a powerful way to study the type 3 algebras. And they showed that what they wanted to know could be recovered from facts about the type 2 algebra. From our point of view, the interest of the cross product construction is just that it's spontaneously generated by gravity. The Kahn-Takasaki results mean that the algebra of observables outside the black hole horizon, taking gravity into account, is really of type 2. In fact, it's of type 2 infinity. This gives a somewhat abstract explanation of why entropy is better defined in gravity than in ordinary quantum field theory, at least in the case of the black hole, since there's a natural notion of density matrix and entropy for a state of a type 2 algebra. One can show that up to an undefined additive constant independent of the state, for any semi-classical state of quantum fields in the black hole background, the entropy computed using the type 2 algebra agrees with the Bekenstein proposal A over 4G plus SL. In my prepared talk, I'm not going to have time to explain this. In questions, if you ask, I'll sketch the explanation. The second paper, the one with Chandrasekharan, Longo, and Penington, I think will be in the archive tomorrow, and has a detailed explanation of this statement in the case of de Sitter space. We'll have a follow-up paper explaining it for the black hole. But for this part of the story, there isn't much difference between de Sitter space and the black hole. So what I've explained now is why gravity turns the type 3 algebra of de Sitter space into a type 2 algebra. So Well, I just made the assertion of Kahn and Takasaki that adding this one operator and one little extra factor in the Hilbert space turns type 3 into type 2. To prove that, most economically, you can simply write down an explicit formula for the trace. It's written in my paper. Again, wasn't planning to really explain it in this talk. That's something else we could discuss a little bit if there are questions later. So the algebra we got for the black hole is actually of type 2 infinity, where the infinity is related to the fact that there's no upper bound on the possible entropy of a black hole. Something similar happens in de Sitter space, but in this case, we're going to get a type 2-1 algebra. Where having type 2-1 instead of type 2 infinity reflects the fact that there is an upper bound on the possible entropy in de Sitter space. Here's the setup. So I've drawn again the Penrose diagram in de Sitter space. I'm hoping most of you are familiar with the diagram because there isn't time to explain it well. The diagram can be chosen so that a given geodesic is on the left boundary or the right boundary. In fact, I think in our paper, it's the right boundary. But we're going to think of that geodesic as the world line of an observer. Usually when you study something experimentally, you want to be able to disturb it and also to observe the results. So what you can disturb is something you can influence. So I can send a signal to a point here, and I can also observe what comes back. So I can do experiments on what's out here. So the green region is the region that the observer can influence and also can study. It's the region in which you can do experiments. It's true that there's a region behind in the past horizon that you can observe the way astronomers do. You can observe it passively. You can't really do experiments on it. And there's a region you can communicate with, but not receive signals from. But the region that you're in causal contact with is the green region. And that's the region we're going to be studying. The green region is called a static patch because you can pick one of the generators of the de Sitter symmetry group to act as time translations of the static patch. And with that notion of what's meant by time translations, the static patch is time independent. De Sitter space isn't time independent in a intrinsic way because it's exponentially expanding. Here's a global picture of the metric of de Sitter space. So there's no intrinsic sense in which de Sitter space is time independent. But for the vantage point of a particular observer, you can define a portion of de Sitter space, the portion that that observer is in contact with. And that portion it can be viewed as being, well, is time independent in an appropriate sense. So it can be considered static. So there's a killing vector field of time translations that's future-directed time-like in the static patch. It's past-directed time-like in the region space-like separated from the static patch. So it goes like this: future-directed time-like here and past-directed time-like here. So let H be the generator of time translations. In ordinary quantum field theory, we'd associate a Hilbert space H0 to de Sitter space and a type 3 algebra A0 of operators in the static patch that acts on H0. However, in a closed universe, the isometries have to be treated as constraints. This means that we should replace A0 by A0H, the invariant subalgebra. A0H, in other words, is simply the algebra of observables in the static patch that commute with H. But that doesn't work. What people who work on operator algebras would say is that the modular automorphism group acts ergodically, and A0H is trivial. It consists only of C numbers. The only way to get a reasonable answer is to include the observer in the analysis. So we're going to take a minimal model of the observer, where the observer is just a clock with a Hamiltonian X. It's physically reasonable to assume that the observer's energy is bounded below by 0, so we assume that X is non-negative. Thus, the effect of including the observer is to modify the Hilbert space by replacing what it would be without the observer by the same thing tensored with L2 of R plus, square integrable functions on the half line of non-negative x. Likewise, we should extend the algebra from A0 to what I call A1. Well, what's A1? We have all the operators we had before, but we also have the operators of the observer. I'll assume that the observer can manipulate the observer's Hilbert space in an arbitrary fashion. So for the observer, I include this Hilbert space B of L2 of R plus, the type 1 algebra of all bounded operators on L2 of R plus. Finally, the constraint becomes the total Hamiltonian of the quantum fields plus the observer. So H plus H of the observer is the total Hamiltonian. The correct algebra of observables, taking into account the presence of the observer, is therefore not A1, but the H-hat invariant part of A1. And essentially, by Takasaki duality, this algebra is of type 2-1, which means there's a notion of density matrix and entropy. And because the algebra is now of type 2-1, rather than type 2 infinity for the black hole, there's a state of maximum entropy. If we assumed that the observer's Hamiltonian was unbounded below, we would have gotten an algebra of type 2 infinity, but that's unphysical. In any realistic model of the observer's energy is bounded below, and therefore we will get an algebra of type 2-1. The state of maximum entropy corresponds to the natural de Sitter space state, sometimes called the Bunch-Davies state, extended in a simple way to a state of the observer. The density matrix of the maximum entropy state is 1, the same as in ordinary quantum mechanics, except in ordinary quantum mechanics, the trace of the identity is usually the dimension of the Hilbert space. So usually in ordinary quantum mechanics, the maximum entropy state has a density matrix that's a multiple of the identity, but not literally the identity. With the usual type 2-1 conventions, the maximum entropy density matrix is literally 1. It has a flat density matrix as first predicted in a Euclidean path integral by Dong, Silverstein, and Taroba. And this is closely related to a result discovered in another way by Banks and Susskind, or primarily by Banks and Susskind. That's something else I can tell you about if there are questions, but it's not part of the prepared talk. Again, facts known from gravity can be recovered from the algebra. I should stress something that I haven't had time to explain. Entropy defined this way is really defined up to an overall additive constant independent of the state. That's because of the renormalization that was involved in defining the trace. So remember, we had to take 2 to the minus n times the ordinary trace. And then we took n to infinity. So we included, well, we divided by an infinite factor of 2 to the n when we defined the trace. So there was a renormalization built into our definition of the trace. And that means that the entropies we define are actually renormalized entropies with an additive constant removed. And therefore, from the type 2-1 algebra, or type 2 infinity algebra for the black hole, we can only discuss entropies up to an overall additive constant. But up to an overall additive constant, these entropies do reproduce expected properties from gravity. So this is analogous to entropy in classical physics. In classical physics, entropy is defined up to an additive constant by formulas like the first law. And you see the first law defines ds, but it doesn't tell you how to determine a constant in S. And I explained in another way why classical physicists had trouble with that. If you change the units in which you're measuring p and x, you could compensate by rescaling rho, but then the logarithm shifts by a constant, and that will shift the definition of entropy by a universal constant. That depends on your units. So the type of entropy I've defined is similar to entropy in classical physics in that respect. To conclude, we've learned that at the level of semi-classical gravity, we can define an algebra A such that the generalized entropy in the presence of a black hole or cosmological horizon, at least in the case of de Sitter space, is the entropy of a state of the algebra. And this has given an abstract explanation of why the generalized entropy is better defined than either term is separately. This algebra does not have pure states, so at this level, there is, for example, no notion of a black hole microstate. Thank you very much.